I want to talk a little bit about Activity 7 today. And the activities always kind of mix the math and art, and I usually like to separate them a little bit and then kind of link them together uh, with the classroom activities. And so, again, here we're just kind of start talking a little bit about Gothic architecture, very important time in uh, in architecture. It's around the 11th century. But Gothic architecture typically has certain types of geometric based designs, and I'll be more specific with that, but it is linked to this buildings that were created in northern France and Britain in about 1110 to 1140, and then kind of spread throughout Europe in different areas and lasted up until like about the 16th century. And but number three here, a study of Gothic architecture is largely a study of geometry. And again, the designs are all made from geometric constructions. And you can do that with just a compass and dividers. And they remember this was back in the 11th, 12th century, so they didn't have computers or calculators or drawing tablets or anything like that. So it was pretty much done very simply with, again, compass and dividers. And if we look at a couple of the buildings, let's take a look at probably one of the most famous ones in Paris. And you may have heard about this one. Actually, last year there was fire in it and burnt a lot of the top, and they're trying to reconstruct it now. It's going to be very long and um, expensive, but this is a very classic Gothic building, and it has to deal with a lot of the structure for the support structure and the windows and entranceways and so on. So, uh, for example, this front door entrance, and you see these arches, and these are called Gothic arches. And uh, what was so important about these is that they were superior to the either circular arch or the beams that just went straight across, say, above a doorway. But before the 12th century, you saw very few buildings over 2 stories. And we have a lot of examples throughout history where, like, the Romans tried to build higher with the types of building materials they had, and then the buildings would collapse. And they thought it was because of the building materials, but it was really the design of the supporting structures that was the biggest issue. And then with these buildings, again, the arches they found out is a very, very strong supportive structure. So you notice these three big arch type supports in the base here. And as you moved up here, again, you've seen these arch supports in here and hallways up and so on. And so that was very typical. And then also these trefoils. So these were ornamentation, but they were again built with just some geometric circles and so on. We have here the rose window. So lots of rose windows, very famous designs uh, in these buildings, and other ones. So they have quarterfoils and different types of arches and so on throughout. So it's an incredible building. Um, I was at the Basilica of Notre Dame in Montreal this past summer, and just an incredible building. This one here in Paris supposedly took about 40 years to the, finish up, and the actual designer um, and guy that kind of put it through, he died before he actually even got to see it finished. But So again, the stained glass windows supported by these type of circular design patterns, and same with the trefoils and so on. And so lots and lots of detail. If you ever get a chance to go into any of these churches or monasteries or basilicas and so on, it's well worth it. Okay, so there's other buildings. If you look through the Salisbury Cathedral, again another famous building, and using Gothic architectural designs. This is the Cologne Cathedral, and um, you can again look at these Deschartres, the castle, and Saint Chapelle. This is the interior. Again, a lot of arches and these types of trefoils or quarterfoils or so on, designs in the windows and so on. All right, so we're going to go ahead on and again, so we talked about Gothic architecture and when it originated, and the again very geometric, and we talked about some buildings and types, again churches and the cathedrals, basilicas, the castles, the monasteries, and so on. And we looked at the 5 famous buildings. And here's a link here that I had downloaded. I actually paid for this. I downloaded it. It was one of the best ones out there I could find. And so we're gonna go to this link here because this is going to show you how to do classroom assignment 1. Now you can use a compass and a ruler, or you could do construct it in Illustrator or so on if you wanted to, since we're not meeting. But it's good reading if you have interest. Again, a lot of students really like this topic and like researching a little further. This is a good paper to look through. You have some different ones other than just Gothic geometry. You have some other different things on here. But what we want to do is on that first page, just kind of go down to the bottom, and I want to click on this OG Arch. And it has very detailed instructions on how to create that. So for example, they say here, construction begins with an equilateral triangle, and simple rule of thumb is which all sides are equal. Now adjust your compass to half the length of the baseline. So that's this length right here, from here to here. You going to then from point A construct a semicircle. So you're going to put your compass point here and then arc it and do a half a circle here from here to here. And then you're going to take your compass point and you're going to create this first with a pencil, just kind of box this off. That triangle, you put a little box. Your compass point will go here, and then you'll arc it down here to create this top part here. Move your compass point over to here, and you're going to arc it in here again. So you really drew 3 lines. You do the semicircle from this point up this corner gives you this arc, and then from B you get this arc, okay? And you pretty much have that shape. And then the equilateral arch, very simple. You need a baseline. So let's say we drew this like 2 inches long, or maybe let's say 4 inches long. And then we're going to put our compass point here and open this up and then arc it out this way from this point. Then we're going to go to this point and we're going to arc it this way. That's it. Just 2 lines. Equilateral arch, arc this way, arc this way. All right. You start with your compass again, this wide from A to B, whatever you make that. You just arc it up, turn it around, arc it up the other way. And I jumped to the other one and said, okay, well, how do you get an equilateral triangle? Well, when you do these two arcs with this baseline, A, B, and C form a equilateral triangle. So that's how you get that first. And we did let's do the trefoil. I'm just going to not go through all these in detail, but you can see you start with an equilateral triangle again, and you move, and then it gives you the directions to go around and work this thing into one of those windows in the buildings. All right, this part in here is the glass part, and the rest of this is supporting structure. And then the rose window, again, they go through and talk you through this. This one's a little more complicated, and eventually you get a nice pretty window there. Okay, so that's activity 1. Those constructions. And then the geometry concept. So we had the kind of art concept, the Gothic design. And one of the important things with those is that there is symmetry, different types of symmetry. And symmetry is very important in design. Probably one of the most important things that people like in designs. And so symmetry, again, there are lots of different types of symmetry. Symmetry in music, symmetry in biology, symmetry in writing, and there's symmetry in lots of things, especially geometry. And that's the kind of symmetry that I'm focusing on here. So symmetry is just that kind of balance in shape. Asymmetry being really not having that kind of balance in shape. And then, so what do we mean by balance? Well, there's 8 different types of symmetry in geometry. So let's go back to here. And in mathematics, if we go down, here we'll see some of those ones. There's what they call reflectional symmetry, and that's reflection about an x-axis, a y-axis, or it could be about the origin. Rotational symmetry, translational symmetry, helical symmetry. There's scale symmetry. We talked about that with fractals when we were talking about similar fractals that have scale symmetry or similar, right? And so on. So there's lots of different types. There's statistical symmetry, probability, symmetric probability distributions, and so on. So we've got lots of options out there. Now, today we're just going to talk about some basic ones. And so explain symmetry in aesthetics and how it influences perception of art. Again, you can kind of read in there, they talk a little bit about that, but basically is that it's kind of like the golden ratio. Why do people like certain proportioning systems? And it's just they do. We can't probably explain it all away, but why do people like symmetry? I don't know, but it does seem to have a balance, and it seems like we like things balanced when we design and we look at things, and shapes seem to have a balance, and so I think people kind of get used to it. It's kind of a comfortable feeling, and it can really influence how people perceive your designs. So if it's something that you're looking again for the masses, what's pleasing to the masses, symmetry is probably a good idea, something to think about. You might want it in. And we talked about how circles are really like kind of the most pleasing geometric shapes. And maybe we can tell why is that circles have, it's the only shapes really that have a lot of different types of symmetry. There's x-axis, y-axis symmetry, symmetry to the origin, and rotational symmetry. So it's really the most symmetric geometric shape that there is, and that may be why people like circles so much. All right, so let's look at this Cartesian symmetry. So if we were working with an xy coordinate axes, and we could talk about point symmetry, and we could talk about line symmetry. Okay, and we're going to go ahead and I'm going to answer these questions in Desmos. It'll be easier to show. And so let's pull that over here and see if I can get these up here. Okay, now there we go. So if you click on this up here in Desmos, remember our little graphing pick right here, click on add and we'll put a table there. So when I put in these ordered pairs, they're going to show up over here. And I'm going to put that first one in 3, 5. So 3, and then move over to 5. And you'll see the point showed up over here, 3, 5. And I'm going to make that a little bigger. Okay. So I can get symmetry about the x-axis, which is this one right here, which means a reflection about it. So what I'm going to type in is 3, -5. And you'll see that reflected in a sense that point, it's the same distance away in the vertical direction. So symmetry with respect to the y or x-axis has to deal with a vertical component, right, being equal. So we got that. And then so I'm going to change these two signs, just the signs. I'm going to take the negative out of here, put a negative over here, up it through my point over here now. So I have symmetry this way about the y-axis. I change the signs here of the x values. These stay the same, right? Different signs. I get symmetry. So symmetry basically is just playing around with changing some signs in points or lines or so on and surfaces. Symmetry with respect to the origin, I'm going to put a point in here. Now I change both of these signs, right? Put them both in here. And then look, I got symmetry around this thing. So it's like I got a line that goes right through the middle into that other point. So these two are kind of like the same distance away from the middle. Okay. So those are the 3-point symmetries, x, y, and origin. And we're going to take that out of there. And let's get on to line symmetries. So here we have y equal to 2x minus 5. Okay, so I have a line. And I want to put another line in. So I do copy, paste. And what happened there, I don't know. So I'm going to try that again. Y equal to 2x minus 5. And let's try to copy that again. And paste that in here. All right. Well, I got two exact same lines. I'm going to change the sign of the y value over here. Make that a negative. And now I have a reflection over the x-axis. Okay. So you pick any point, like this point right here. It's being reflected also down here on the other side of the x-axis. If you got a point up here, it's also going to be one down here, here and here. So that is all the points getting their signs changed, right? All the y values change all the signs, and that's what we essentially did here. All right, I'm going to take that out, put a negative in front of the 2x, and see what happens. I get reflections this way. So I got a point there. That means I got a point right on the other side of this y-axis. Got one here. That means I got one over there, right? Any point on this line is going to have another one over here, right? So that's y-axis symmetry. And then if I put the negatives in for both, I get reflections about the origin, okay? So this point here reflects through the middle, and it's down here now, right? You got one of those. Here's one, it comes down through the middle to there. Here's one, it comes down through the middle to here. Like this one is a reflection of this way down here, okay? This one up here comes through the middle, and it's reflected like this one right here. Gets reflected through the middle, and it's right there. Okay, so good. And of course, there are parallel lines. So there's our symmetry. So classroom assignment 2, draw some simple pictures with Desmos that have reflective symmetries and label this. So you're going to kind of do basically the same thing that we just did. And let's just do a couple more examples in here. I'm going to take these out. And so let's try some different ones. Let's do y equal to let's say x squared plus 1. Right? Now, if I want to reflect it about the y, I can put a negative right here in the front. Okay. Oh, so I got the reflection now, right? So you take that back out. I'll put the same equation in. Put the negative in front of this one. And now we have symmetry, right? With this design so far, you can add other stuff or whatever to it. So we got that. We could actually switch these around. Let's do some new functions here. I'm going to take and let me just paste that again in those. Okay. So what I'm going to do is switch around in these the x and y variables. So this is going to be x, y, and this I'm going to change to x and y. And whoops, negative. Oh, forgot my negative. There we go. So I got a kind of a neat thing going there, and I could get a design, put a little box in here, maybe stop these. Remember that you can restrict these values. For example, let's say this black one, and we can do let's see, 2, and then greater than, less than, x, less than, oh, let's just do that. Let's just do actually and x greater than 2. All right, so, and I could do and this one, the red one, x less than, there we go. And less than -2. All right, so, and we could cut these off, again, using the restrictions here, and put something in, some lines in or something in here, and we have like a design, or we could just put some lines to here, up and down. So y equal to -2, and that is, whoops, x, and x equal to 2. And again, we could cut these off at somewhere. Maybe we just want to take this part right in here, this to here, and something going out that way, or so on. Okay, so that's got symmetry. If we wanted to get something symmetric with respect to the origin, we could just change both of these signs, right? Negative and negative, and we shut that one off. And it's the exact same one. So this one is let's do the original. Okay, there's the original. And I'm going to take and put a negative here, so I can just see both of them, right? So I put the negative, right, in front of both of those, and there we go. Negative in front of y, negative in front of the x, and it looks like a reflection, but it actually is. If you look at these points go through the origin and connect with this one with this one, this one with this one, and so on. And one way up here, it connect with one way down here, and so on. Okay. All right, so classroom assignment, and now piecewise defined functions. Basically, just to not get into the technical math part of it, but basically it's just what we had just done. We were creating some different functions. We had 3 or 4 functions here to create a design. That's a piecewise defined relation, and we had all these functions we were trying to use. We had a bunch of pieces we used in part of one, and we were going to use a part of another one. And so we had different pieces in there. So we have multiple functions to create some kind of design. All right, so, and if they're functions, they're special properties. If they're relations, right, then this is more of a relation. But parametric equations, so this is really the big math concept. This is the most important one for creating visuals on a computer screen. Parametric equations, and again, what they are is that you have one independent variable and then 2 dependent variables, or more actually. But in this case, we're going to look at this right here. These would be considered parametric equations, and I'm going to show you an example. Because I have x is a function of t, and y is separately a function of t, and they're different functions. So y is not dependent on x like in a typical Cartesian coordinate plane. So basically, what we're trying to get at here is that in the Cartesian coordinate plane, you have points where you have like x, comma y, and you have some function like y equal to 2x minus 1. And what you do is you have 2 numbers here, okay? So you got 2 different variables, but this one is really dependent on this one, meaning that y has to be a particular value given the x to make this thing be true. So if we let x be equal to 1, okay, then we would get y equals to 2 times. See, I have to figure out, I got to put in x here, and then I can figure out what y is. So I had to put this in here first. 2 times was 2. 2 times 1 is 1, so x is 1, y is 1. All right. Now, with parametric equations, then we have something like this where my ordered pairs, x is equal to some function of t, and y is equal to some function of, this is f sub 1, f sub 2 of t, okay? So we could pick a couple examples where x is equal 2 times r plus 1, and y is equal to r minus 3, right? Now these r's are the same, but see, x and y is totally independent of x. No matter what x is here, x comes out to be, y, it depends on its own little function here, right? So if we let r be equal to 2, then we would have, and let me just, we have x would be equal to 2 times 2 plus 1, and y is going to be 2 minus 3. So we get, that's going to be 4 plus 1, right? Or 5. And then y is going to be equal to negative 1. So that's how we get the ordered pair. We still get an ordered pair. I get 5 comma negative 1 out of this thing. And so what's so good about it? It seems like a lot more work to do what we did before, but in reality, this allows us a lot more variability in what we can design. In fact, you're almost endless on what you can do with parametric equations and trig functions. So we're going to take a look at what I had written over here. And so this is saying, all right, let's take x, write it with cosine, y with sine. Okay. All right, so we're going to use the trig functions because, again, they're just better, right? They're just a great class of functions for us to do some designs with. And we're going to start out here. And again, the Desmos, we don't write the x equal to, we just put in the other part. A plus r cosine t, comma, b plus b plus r sine of t. There we go. So we really just put in an ordered pair. We put the x and y like we were doing a set of ordered pairs, x comma y. And let's go ahead and add the sliders. That is it. Now, I'm going to change this from 0 to 2 pi. And I want r to be, and we can leave it at 1. I want this to be 0. And I want this to be 0. Okay, so we've been talking about circles. We looked at circles with the Cartesian coordinate plane and then with polar coordinates. And now we're using parametric equations. And So we were able to move it around a little bit and not do else much with it with the XY plane. The polar coordinates gave us a little bit kind of interesting more shapes, and we had super ellipses and things like that we added in. But these, again, we can create circles, and I'm going to make that a little bigger. So these will move it around, okay? So I can go to the right or up and down. There we go. The B, this is the first house. It's with the Y value. This is with the X value here. So the A is the X value. And so we can move it anywhere we want, right? So that's a good deal. Pretty simply, that's going to be our center, right? 2, 2 is going to be A and B. So that makes it nice to work with. And then R is the size. Now, how do we get different shapes is, you have to change. Now in the front here, I could put, let's see, let me put a parentheses, oops, I'm going to throw in all right. I messed up my sign, my something in here got messed up when I hit that button, so I may have to just type this all right through again. A plus R cos T, B plus R sine of T. I don't want this here, so I'm going to have to add them in, but it'll take a second. So again, what I'll do is put in something a little bit different. A plus R cosine of 2t. Okay, 2t. There we go. Comma. And then B plus R sine of t. Okay. Oh, there we go. All right. And again, I want to change this to 2 pi. And we'll notice we've got a different shape this time. So I threw a 2 in here, and I've got something a little bit different looking. And again, if I change, the A moves it, right? We can move that thing around. The R, okay, again, let's change the sign, and the B, I'll move it up and down that way. So now let's look in here, and this T in here, let's put a 3 and see what happens. Okay, so I get another kind of shape that loops around. And you can continue to kind of play around with these things and see what you come up with. You can change these trig functions or tangent of 3t, and then we got a different kind of shape and so on. So All right, so let's bring that back over. So that's kind of classroom assignment 3, is to get those in that form in Desmos, and kind of just play around with some of the parameters and so on, and get a feel for that kind of a function and what it looks like. Okay, so Sri Yantra, there's a YouTube here. There was a movie called The Last Mimsy, and one of the things in it is it had a Sri Yantra, which is kind of like a lot of people related to a mandala. And a Sri Yantra is a for religious a medium for getting to a higher level, and that's what the movie was about. Is they had these, so visually they showed what the Sri Yantra looked like, and I'm not going to play the trailer, but you can go ahead and look at the video. But here's what the Sri Yantra looks like, and it has to deal with a lot of symmetry, um, and these 9 interlocking triangles. And so what we wanted to do was just look at this as an idea of kind of a pattern that was kind of famous, and put this back over here. And it comes back through the movie several times, and then but there's something that relates to this that's very similar. And the Sri Yantra had been around for a long time, but then they started to do some experiments with sound. And this TED Talk, again, is something that you really want to listen to here. And what happens is the sound, if you take sound and vibrate a plate with sand on it, uh, it will turn into a geometric shape. And if you increase the frequency of the sound, it will continue to change that shape and so on. So this idea of we had kind of an idea of maybe something like this, thousands of years ago, but it's very interesting to see how the symmetry in geometry relates also to music. So we can tie designs with music. So the physical designs with the sound, the vibrations, and so it's a pretty neat connection, very creative idea. Cymatics is fairly new, but it's a very interesting study, and so it's very, very new. And it doesn't want to. Oh, here it is. Okay, so they talk about here can Sri Yantra be created from the Om sound, and this is kind of why I said, is there a link between the Sri Yantra and this vibration of creating that? And they said yes, that is possible. And then here's some other visuals that were created with sound. Okay, and then you can go through and look at this science of cymatics. But you'll notice that sound and vibration emanate some very really cool looking pictures. And there's a lot of symmetry involved: X and Y axis, origin symmetry, and rotational symmetry. So some very, really, really cool pictures. And again, these were created not by hand. These were created with vibrations. Um, and you can watch the videos on there and so on. So it's just a neat application I wanted to show you. It kind of links in what we're talking about. Okay, so let's go on to and create a design in Desmos using 2 or more functions. So that we talked a little bit about before. And then I want to go into the CalcPlot 3D, and it's kind of the last thing we'll talk about